Therefore, using Green's function we can obtain solution for equation 3, which is so phi of A is this. So now I am essentially going to get P prime of A is a solution that I want, that is P prime essentially, and this is Green's function is minus 1 by 4 pi, right. So it is minus 1 by 4 pi integral, volume integral, and then I have the entire source, right. I have also this 1 minus B by A that is there, but before that S of B I am going to write. So I get minus of this entire source term, which is 2 dou ui bar of B by dou xj. I am writing the mean strain part first here, okay, and then dou uj prime of B by dou xi. So this is the second term on the right hand side that you had, the mean strain component, and that is at the point source location B, dou uj bar by dou xj, dou uj prime by dou xi, that particular component, plus I have the Reynolds stress component, which is dou square by dou xi dou xj of, I have ui prime of B and uj prime of B minus the Reynolds stresses, which is ui prime of B, uj prime of B average. I have taken minus here, minus of the bracket, and therefore the sign changed. Earlier it was Reynolds stresses minus these two product of the fluctuation. Since minus is taken out, it has become the other way, okay. So I have this, the entire part, and then I have dB cube by B minus A. So this is my source term here, right. So this entire part here is nothing but S of B, the source term, right. G of A comma B is here, minus 1 by 4 pi B minus A dB cube, that volume integral. So this is the entire source term that I have replaced here, S of B, a complicated source term indeed, where I have the rapid and slow parts, right. So this is your rapid part, this is the slow part. Sorry, density, yeah, so P prime I can, it's a constant, so P prime I can put it as rho here, P prime by rho, I keep it here constant. Okay, so at least now we have an expression for P prime at a location A depending on point sources, which is Reynolds stresses and mean strain at B, okay. So now we have to, this is still not complete modeling part, we still have right hand side, the source term is an unknown, I have no access to this in the, when I computing the Reynolds stresses, so I need to still make some modeling assumptions, and first thing is to see in a modeling whether I can get rid of some terms. For example, in the slow term, can I make some assumption to get rid of one of the term in that? Can you assume a flow where some terms vanish in the slow part, like statistically homogeneous flow? If flow is statistically homogeneous in all three directions, what will happen to the gradient of this average term here, this particular component? It will be 0. So I am going to assume homogeneous turbulence, okay. These are model assumptions, so I am going to start with, so let us call this equation 4, So let's make some model assumptions. Model assumptions. So what is that? Is that first thing is I am going to consider homogeneous turbulence, statistically homogeneous turbulence, statistically homogeneous turbulence, which implies I have, let's say, dou by dou xi of some averaged quantity is 0, where I can be I equal to 1, 2 or 3, 1, 2, 3, not or and 1, 2, 3 I would say, because I need fully statistically homogeneous flow to get rid of that particular component. So the consequence of this is one term will go away. Okay, this is the first model assumption, statistically homogeneous. And I can make another assumption is that on the rapid part, if I am going to assume that this mean strain dou ui bar by dou xj, if I am going to say that as I walk along, this is exhibiting small changes, what does that imply? It implies that the mean strain is almost constant. When it is constant, I can take it outside the integral. So I would like to assume that it is constant or almost constant. So I am going to say that spatial variation of, let spatial variation of dou ui bar by dou xj be small, that is dou ui bar by dou xj is almost constant. I would like to do that so that I can take it outside the integral. Alright. So with these two model assumptions, let us see what would happen, right. So what would happen for the first one is that this particular term in the equation 4, okay, in equation 4, the dou square by dou xi dou xj of this ui prime of b u j prime of b, this average term will be 0, the consequence of the first assumption in equation 4, okay. And the consequence of the second one is already I said this will become almost constant, that means this term dou I bar by dou xj can be taken outside the integral. These are the consequences of two model assumptions here. Okay, so I am going to do these two and get an expression for pressure strain rate. Now since I have P prime by rho, I can multiply the remaining part and average to get the equation for pressure strain rate, right. So multiply equation 4, okay. So I am going to, let's copy this particular term here, or it's okay. Let's go to, so multiply equation 4 by dou ui prime by dou xj plus dou uj prime by dou xi and Reynolds average or ensemble average. So what will this be? So I am going to get P prime of A by rho, of course, the constant value, multiplied by dou ui prime of A by dou xj plus dou uj prime of A by dou xi average. So now I have got an expression for it now, which is now equal to the right hand side part, which is so it's, if you go back and see, it's minus 1 by 4 pi. So I can essentially get plus 1 by 4 pi integral, volume integral here, and then I have the source term here, which is 2. Now if I just go back to the previous slide, you can see here these are point sources at B. I am now multiplying this with the solution at point A here, okay. So I cannot multiply on the right side and still call it ij index, because right now it is, one is a function of B, the other one is a function of A. So I need to change the indices on the right hand side. Since on the left hand side I have multiplied by the velocity fluctuation gradient dou ui prime by dou xj, on the right hand side I cannot use I and j. So I am going to change to something else. Anyway, I and j are repeated, it is eventually sum of 9 terms. So I am going to use some other index here for consistency, okay. So I am going to do 2 dou uk bar by dou xl. So I and j replaced by k and l of B, this is the point source, and dou ul prime of B by dou xk, plus I have the dou square dou xl dou xk of uk prime of B and then ul prime of B. This is my entire source. Okay, wait, entire source multiplied by this particular term on the left hand side, right. So I have dou ui prime of A by dou xj plus dou uj prime of A by dou xi, and then the average term, and then I have this dB cube by B minus A, the delta function. So note that this particular part here is a function of A, not B, and therefore I can push this inside the integral. The integral is valid for the point source B, but the what I have multiplied is a function of A, so it can go inside the integral, okay. So you can take note here. So here I is set I comma j or replaced with k comma l, okay. Since this is a function of B, and here this part, so here since this is a function of A, it can be moved inside the integral. So this is my source term, right, S of B, the entire source. Okay, so the left hand side I have what I wanted, a pressure strain rate term. So now the pressure strain rate, at least I know now that what it will depend on the right hand side if I want a solution for that one. So I can split this again into the two parts, that is the rapid and the slow parts. So the left hand side is equal to, so I get the first rapid part, which is 1 by 2 pi, okay, and then I am moving the integral here, the mean dou u k bar, the model assumption dou xl of b integral v dou ul prime of b by dou xk multiplied by dou ui prime of a by dou xj plus dou uj prime of a by dou xi. Averaging dbq by b minus a. So that is my rapid part here, rapid term, and then the slow term, which is plus 1 by 4 pi of integral v dou square by dou xl dou xk of uk prime of b ul prime of b multiplied by dou I prime of a by dou xj plus dou uj prime of a by dou xi average dvq by b minus a. This is your slow term. Let's call this equation 5 here. You're all with me so far? Okay, fine. So now we would like to make another approximation or consideration. So we will take term by term to model now from up to this. So we have arrived at equation 5 by making two assumptions: statistically homogeneous flow, homogeneous turbulence, as well as considering mean strain is nearly constant. On the left hand side I have pressure strain rate term that is equal to these two, what I call rapid and slow term. So if I am going to consider only the rapid term, okay, so consider only the rapid term now, or I can say modeling the rapid term. So term by term we will model this. So what I do is, let's consider only one component. This is actually 2 here, right? This is multiplied plus, so sum of 2 different terms. So let's consider one term and see what will happen to it. Okay, so consider one term in the rapid part of equation 5. So let's say I take dou uj prime of a by dou xi and dou ul prime of b by dou xk. Okay, so now if I use product rule here, I'm going to use product rule. What will this become? If I use product rule, I get dou by dou xk of ul prime of b dou uj prime of a by dou xi. So if I use product rule for this, I am going to get the left hand side term and one more term. So this will be minus then, correct? So minus of, I am going to get essentially ul prime of b dou square uj prime of a by dou xk dou xi. I have just used the product rule here. So if you take product rule only for this particular term, it will be sum of this and this. That's it, nothing new here. Okay. So if you look carefully onto the right hand side, these are two terms, and the extreme right part here, uj prime of A, that is a function of A. So for A I have indices I and j, right, but there is k and l which is the index for the source B. So dou uj prime of A by dou xk should be 0, because one is a function of A, the other one is not, right. So I can write here, so this particular term goes away, or I can rewrite this as, okay, so I can call this dou by dou xi of dou uj prime of A by dou xk. So this term will be 0. That's because since uj prime of A is not a function of B, okay, and dou by dou xk is applicable to only functions of B, the gradient. So dou by dou xk of this particular thing is 0, this goes away, so I have this particular term. I can simplify this further. So this again I am going to use product rule. Using product rule again, I would get dou by dou xk of, I am going to push this dou ul prime of B inside the derivative using product rule. So I would get dou by dou xi of ul prime of B uj prime of A, okay, minus uj prime of A dou ul prime of B by dou xi. Okay, so dou by dou xi of, this is I, dou by dou x of ul prime of B uj prime of A minus this particular term. So again the same argument, this ul prime of B is a function of B, but xi or index I is used for solution A, right, same argument, this goes to 0, because similarly ul prime of B is not a function of A, and dou by dou xi is applicable functions of A. So that goes away. So essentially that means I have now this particular term is nothing but the left hand side here, which is dou uj prime of A by dou xi dou ul prime of B by dou xk is equal to dou square by dou xi dou xk of ul prime of B uj prime of A. So if you see, we have somehow brought a relationship between the rapid term, which essentially has a mean strain, right. In that particular term we have said the rapid term is now somehow related to a mean strain, that green particular thing that I have written, dou ek bar by dou xl, right. And then this particular term, that is in the rapid term here, if you see, I have a mean strain plus I have another term, the nature of that term was not visible. Now if I just applying product rule twice, I reveal that each of this term if you take one of this or the other one, you can test it is going to be the same. You will get a relationship like this. So, and there is an average here, right? So, this essentially nothing but this particular term, if I average this, it will be this. Right? So, that means the pressure strain rate is related to mean strain which I have access and Reynolds stresses. So, I am coming closer to modeling at least one term, the rapid term, and I have access to both Reynolds stresses and the mean strain rate. Okay. So, therefore, I can say that from equation, okay, so this previous equation, let us call it this as equation 6, right, equation 6. So, from 5 comma 6 I can say that pressure strain rate or the rapid part in pressure strain rate is depending on the mean strain and the Reynolds stresses. From equation 5 comma 6, okay, it is clear that this pressure strain rate rapid term, we can call this, let us say, pi ij rapid, let us say, okay, like this. This term is a function of dou u k bar by dou xl comma uj prime ui prime average, right. So, these are known to me, known mean strain and Reynolds stresses, ul prime, right, this is, was that ul prime, uj prime ul prime, yeah, okay, ul prime. These are known terms to me. So, I can make a model now. This particular model for the rapid has a name, it is called IP model. It is a very popular model used in commercial codes also. So, the pi ij is called IP model. This IP model, which means isotropization of production, that is IP. There is a reference for this, which is a reference article and 1970. This is a reference article. So, what this model is doing is essentially, the modeling philosophy is that the rapid term partially counteracts the production rate term, okay. So, rapid term partially counteracts production term. So, if you recall, pressure strain rate role is basically to redistribute, okay, and we are trying to relate it to the production rate because production rate has Reynolds stresses and mean strain, and we have established a relationship now that the rapid term in the pressure strain rate is a function of Reynolds stresses and mean strain rate, and therefore, the model itself will be like this. So, the pi I comma j, let us call it R, or you can say rapid also. In some literature, you will just see R as the subscript. This model will be minus C2 rho multiplied by Pij minus 2/3 Pk delta Ij. So this is the model for one part. So there is no, this is not a complete model. So slow term also has to be modeled. So the pressure strain rate term will have two models, one for rapid, one for slow. So this is the pi ij model term. Okay, this is the model term, and this may look little strange. Why is this production rate coming? But if we expand it, we will get back to the original part, which is minus C2 rho of what is Pij? Pij is nothing but your minus ui prime uk prime. You can go back and look at the equation. You will get dou uj bar by dou xk minus uj prime uk prime average dou ui bar by dou xk. This is your Pij minus 2/3 Pk, also you can substitute. So both Pk and Pij terms are functions of, this is your Pij and also this Pk. So both are functions of the mean strain rate, right? So dou ek bar by dou xl comma uj prime ul prime. That is what we have accomplished here. So the rapid term depends on mean strain rate and Reynolds stresses. This IP model is popular. You can use this, and the model constant is C2. If I C2 and density, if I am going to set equal to 1 here, and if Pk is 0, then this pi ij rapid essentially becomes Pij, right? So this pi ij term is actually taking away what production rate is doing. Even in a canonical flow, we have seen that production rate, let's say, is in only direction along the x direction, then y and z it is redistributing. So this pi ij is taking away whatever is being produced. In the absence of, let's say, if C2 is 1 and Pk is 0, pi ij rapid becomes minus Pij. It is essentially taking away everything. That is the whole isotropization of production meaning. Okay, so we have to still do the slow term. We can take a break till, and if you have any questions,